start recording. Okay. All right. So we talked about, we left off on Monday before lab, talking about QC, that reaction quotient, and how calculating QC will tell us whether or not the reaction needs to go further forward into to form more products, or needs to go backwards to reform some reactants. Okay, but once we're at equilibrium, equilibrium is usually achieved relatively quickly, within a few minutes of a reaction starting. Not always, but many times that's the case. And once that equilibrium is set up, we want to know the concentrations in our solution. And so in order to do that, we have to go to our equilibrium constant, Kc, or PC, or Kp, if we have pressures, but usually we're talking about concentrations. So in calculating equilibrium concentrations, there's a few steps we need to take in mind, right? The first is that we need to express all of the equilibrium concentrations in terms of their initial concentration and then one unknown, right? So, for example, if water breaks down into hydrogen and oxygen, for every water molecule, we're going to get 2 hydrogens and 1 oxygen atom, right? And so this single X, right, that would mean that if we break apart one water molecule, so that's X, we get twice as many hydrogen atoms. So the hydrogen value would be 2X, right, twice the number of moles. And then the oxygen value, we only get 1 oxygen for every water molecule, so that would just be X again, right? So even though they're all different unknowns, they're all related to one another because of the way chemical reactions work, because the fact that matter can neither be created nor destroyed. If we break up one molecule of water, we have to end up with 2 atoms of hydrogen and 1 of oxygen. And so that's where the single unknown X comes from. So the equilibrium constant expression, right, that's our Kc expression. We're going to write that in terms of those equilibrium concentrations. We do that normally, but now instead of doing it in terms of just brackets with a symbol inside, we're actually going to plug in some numbers, and we're going to talk about the X's in a minute. If we know the equilibrium concentrations, we can solve for the equilibrium constant. If we know the equilibrium constant, we can solve for concentrations. We can't do both, right? If we don't know the concentrations and we don't know the equilibrium constant, we're kind of out of luck, okay? So we plug everything into our Kc expression, and then we solve for our unknown. And once we have our unknown, we'll calculate the concentration of all species. And so we tend to do this in something that we call an ICE table. And so I'm going to do the water example. So let's say this is an equilibrium with 2 atoms of hydrogen and 1 atom of oxygen, right? And I'm not talking about diatomic elements for now. We're leaving these as atoms. And so our initial concentration of, let me write it out a bit more since this is the first time we're doing this. So we have our initial concentration. We have our change. The change will always be in terms of X. And then we have our final concentration. Okay. So let's say that we started with 1 molar water, right, for example, no hydrogen and no oxygen atoms. Our change, well, we're going to, if we have no product, right, we're going to have to shift to the product side in order to reach equilibrium. And so we lose some of our reactants, but at the same time, we gain some of our products. Okay. And so it's a minus X on the reactant side. It's a plus X's on the product side, but we have to take into account those coefficients. And so that 2 comes down here. And so we get plus 2X and plus X for hydrogen and oxygen respectively. And so our final would be 1 minus X for water, 2X, 0 plus 2X is just 2X, 0 plus X is X for our products. And then if we know the value of Kc, we can just set this equal. Well, we know it's products over reactants raised to their coefficients. And so the concentration of hydrogen, well, let me write it out this way first. Concentration of hydrogen squared times the concentration of oxygen divided by concentration of water. Well, this is 2x squared. This is x. And this is 1 minus x. I really don't need those brackets up there. These are not concentrations. These are just variables for now. And then it's just a matter of solving for x. Okay. This one is a little bit more tricky, just this example, because we get an x cubed term in the top, right? This becomes 4x cubed. So that's kind of a tricky one. But the example that we're going to do is a little bit more straightforward. So here we have hydrogen and iodide forming hydrogen iodide. That gives us an equilibrium constant of 54.3 at a temperature of 430 Celsius. We're going to calculate the concentrations of hydrogen iodide and hydrogen iodide at equilibrium. Okay. So I'm just going to sort of build my ICE table. So again, this is initial, change, and equilibrium, ICE. It gives us initial concentrations of 1/2 molar for both hydrogen and iodide. And we start with no HI. Now I did remember to take into account the fact that this was a 1 liter vessel, a little bit easier to do this time. We ended up on Monday where I forgot to convert my moles into concentrations to plug them into K. And so remember K requires concentrations. And so you have 1/2 mole of H2, 1/2 mole of I2 in a 1 liter container. So again, it's clear that we need to shift products. We don't have any products. And so the shift is going to be to the right. So it's going to be minus X for hydrogen, minus X for iodide, and plus 2X for HI. Again, that the fact that these are both 1X come from the fact that the coefficients there are 1. The fact this is 2X comes from the fact that the coefficient for HI is 2. Okay. Now this equilibrium line, I'm going to go ahead and write it in terms of X. And so now we have 0.5 minus X for H2. We have 0.5 minus X for I2. And 0 plus 2X is just 2X for HI. So we go over and we set everything equal to Kc. Kc for us is equal to 54.3. And that's equal to products raised to the power of their coefficients. So 2x squared divided by 0.5 minus x for hydrogen and 0.5 minus x for iodide. Well, now this is actually pretty easy because we have a squared term on top. And if we look at this, right, this is just 0.5 minus x squared. Okay. And so because we have a square on the top and a square on the bottom, the easiest thing to do, take the square roots. Right? So So if we take the square root of both sides, we need the square root of 54.3. .37 is equal to 2x divided by 0.5 minus x. Rearrange, get x by itself, and we're going to solve for x. I don't know where the times 10 came from. Okay, so we rearranged and we solved for x. We got x is equal to 0.0393. Now, remember our Kc value is unitless, but that x represents concentration, and concentration has a unit. And so we need to remember to tack on our molarity unit onto our x value. Okay, well, that's not quite where we need to end up. The question was to calculate those equilibrium concentrations. And so the concentration of H2 is 0.5 minus x. And so 0.5 minus 0.393, and that's 0.107 molar. That's the same for I2. We start with the same amount, and it's also 0.5 minus x, so 0.107 molar. And then the concentration of HI is just 2x, and so that's what is it, 786 molar. Okay. Now, if you ever want to check your work when you're doing a problem like this, what you can do is you can just recalculate K. Right? You have equilibrium concentrations. Those concentrations should still give you your K value. And so if we do that very quickly, 0.786 squared divided by 0.107 squared gives me 54.0. That's pretty close. If we had given it one more sig fig, we might have gotten it bang on, right? So that's using an ICE table. And again, this one was pretty straightforward because we could use that trick of square rooting the top and the bottom in order to give us the value for x. So let's do one that's a little bit more involved. Okay, so we have the same reaction, we have the same temperature. If it's the same reaction, the same temperature, what else is the same?
Pressure.
We have the same equilibrium set up. We're still at 430 degrees C.
Is it the pressure?
Have I muted you all again? Okay. Yeah, my Zoom went to the wrong speakers. Okay, so somebody, again?
Pressure.
Pressure, sure, maybe. If we have the same equilibrium and the same temperature, then we should have the same value for Kc, 54.3. Remember, equilibrium constants depend on temperature because they depend on those rates, and rates, we say, are very temperature dependent. So in this example, we have a little bit of starting material for everybody, not just our reactants. And also we have, they're not exactly the same, so we won't be able to use some of those tricks. So here's our ice table. And we have 0.00623 concentration of H2, 0.00414 concentration of I2, and 0.0224 concentration of HI. Okay. Well, now that we have some product, it's not very clear which direction our equilibrium needs to shift in order to reach equilibrium, right? Which direction our reaction needs to go. And so how do we determine whether our reaction needs to go toward the reactants or toward the products? What do we need to calculate?
Q.
Yeah, absolutely. We need to look at Q. And so if we calculate Q, concentration of products of reactants, 0.0224 squared divided by 0.00623 times 0.00414. So somebody do that math.
$19.45.
That sounds good. And how does that compare to Q, to K? Sorry, Q, is it greater than, less than, equal to? Well, it's less than K. If Q is less than K, which direction do we shift? Toward the reactants or toward the products?
Dr. Davis, I didn't get that answer.
I did. Did you square your 0.0224 up top? Q less than K, which direction do we shift?
Products.
Yeah, we need to shift to the products, which means we need a plus X on our product side. So plus 2X there, minus X for each of our reactants. So we end up with 0.00623 minus X, 0.00414 minus X, and 0.0224 plus 2X. And so we set it up again, 54.3 equals 0.0224 plus 2X squared divided by 0.00623 minus x times 0.00414 minus x. Now this is a lot of foiling. Do you remember foiling? First, outside, inside, last, right? And so we have to do that on top and bottom. Then we're going to collect like terms and all that kind of stuff. And so what we end up with when we do that foiling, so I'm going to put in here foil. We're going to foil the top and foil the bottom. We end up with 5.02 times 10 to the negative 4. That's our 0.0224 squared. Plus 0.896 times x plus 4x squared. On the bottom, we end up with 2.58 times 10 to the negative 5th minus, let me erase that. Eraser is berserk. Minus 0.0104 times x plus x squared on the bottom. Okay. So, hope you remember your algebra. Right? We have our first outside, inside, last on the top, our first outside, inside, last on the bottom. We're going to multiply the whole bottom across times 54.3. Then we're going to get everything to one side so that we can solve for the quadratic. I'm just going to give the final equation here. We end up with 50.3 times x squared minus 0.654x plus 8.98 times 10 to the negative 4 is equal to 0. So we need to solve for the quadratic. We need to solve the quadratic equation in order to get our answers for x. Right? And so remember that x is equal to our quadratic equation. X is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. To know what a, b, and c are, those are, a is always associated with x squared, right? So this is a. B is always associated with x, so this is b. And c is always the constant that has no x. So we plug all that in. A word of warning here. This b value is 0.654, not negative 0.654. That negative sign out front doesn't have, the negative sign out front means that the b value is negative. And so when we plug it in, we get negative b, and so negative b is positive 0.654, plus or minus the square root of b squared, so negative 0.654 squared, minus 4 times a, 50.3, times c, 8.98 times 10 to the negative 4th, all over 2 times 50.3. Okay. If you haven't done the ALEKS yet, you'll know that there are a couple quadratic examples in there. And so hopefully you get some good practice with the quadratics this week. This is all x is equal to. And so we get two values for x when we solve all this. We get x is equal to either point, oops, I don't need to, either 0.0114 molar or X is equal to 0.00156 molar. Okay. Occasionally, we'll end up with a negative root and a positive root, and then it's easy for us to throw away the negative one. Concentrations can never be negative, and so X can't equal a negative value. Since we have two positive values for X, we need to look at whether or not one of the two will give us a negative value when we plug it into our equilibrium expression. So I'm going to write up here H2 plus I2 in equilibrium with 2HI. And I'm just going to copy over our equilibrium line from the slide before, which was 0.00623 minus X, 0.00414 minus X, and 0.0224 plus 2X. Well, if we look at the hydrogen and iodine concentrations, this value of X is way too big, right? This gives a negative concentration. And so it can't be that X, right? 0.00623 minus 0.0114 is a negative number. Right? And so we have to use this value for our X. And so the concentration of H2 is 0.00623 minus 0.00156. And that gives us 0.00623 minus 0.00156. That gives us 0.00467 molar. For I2, 0.00414 minus 0.00156. That's 0.00258 molar. And then for HI, 0.0224 plus 2 times 0.00156 is 0.0255 molar. So that one, so we saw essentially the shortest option where you can just take the square root of the top and the bottom, rearrange, solve for X. That's the easiest option that we will see. And we saw sort of the very longest option, the one where you have to do the quadratic. You have to FOIL both the top and the bottom. You have to do the quadratic, and you have to decide which root to throw away. So we did sort of both ends of the spectrum in terms of difficulty. Okay, any questions about how to work an ice table like this? We're going to see this a lot more in chapters 15 and 16, and so we're going to revisit this, but just this introductory equilibrium chapter 14, being able to plug in and solve these ice tables is going to be an important piece of this material. Okay, well, if there aren't any questions, again, just refresh yourself on that algebra for foiling and for solving the quadratic, and you'll be okay for this part of the quest. All right, so this last part in chapter 14 deals with Le Chatelier's principle. And we talked about this in lab a good bit on Monday. So let's go through sort of the details of it now. So Le Chatelier's principle, as we mentioned in lab, is how our system it describes how a system responds to an external stress. Maybe one of the things that I saw a lot of groups kind of getting caught up on Monday was the fact that when we talk about what an external stress was, it was easy to confuse that external stress with what the internal system, the actual chemical reaction, was doing. And hopefully in these next couple slides, we'll talk a little bit more in detail about how we separate out what's external and what is the system reacting. And so the first thing, and what a lot of Le Chatelier describes, is a change in concentration. And so that's the first part of his description here. So in this reaction, in this example here, we have some ammonia, and we have some nitrogen, and we have some hydrogen. Now these are all flat lines over time, which means this reaction is already at equilibrium. Right? So it has reached equilibrium, and then at some point, an external stress, that means somebody in the lab added extra ammonia to that container. Right? Somebody just took a little, ammonia is a gas at room temperature, and so somebody took a little syringe full of ammonia gas and injected it into that container, and all of a sudden the concentration of ammonia is large, and so that's the external stress. So if we're thinking about this particular reaction, the concentration of ammonia is increased the reaction that the system's going to do, right? So this is external. The next one is the requirement. Okay. And so the system will react by reducing the ammonia concentration and then this last bit is the action or the shift. The system will convert ammonia, NH3, into nitrogen and hydrogen. Now, just given this graph, we don't know whether ammonia was a reactant or a product. If we did, we could be a little bit more specific about how we're converting product into reactant or reactant into product. But generally speaking, we're converting something into either a reactant or a product into either a product or a reactant. So that's a concentration change. When we talk about how things are going to shift, right? If we increase the concentration of the product, So that's adding something on the right. Again, I think about it like a bicycle. If you add product, that's like pushing forward on the right handlebar. We're going to shift that equilibrium back to the left, back toward the reactants. If we decrease the product, so strike that through, and now we remove it, that's like pulling back on the right handlebar, the product handlebar, which is going to shift our bicycle, shift our equilibrium to the right. Okay. For our reactant side of things, if we're increasing the concentration of one of our reactants, we're pushing that handlebar forward, we're going to shift from reactants to products, so to the left, and then if we decrease, we're going to shift back to reactants from products, so shifting right. It's all about reacting to whatever the stress was, right? So if the stress is decreasing the concentration of one of the reactants, the way that it overcomes that decrease in concentration is to try to increase it back to close to what it was, as close as it can get. And it does that by, well, turning some of those products back into reactants. Now, we talked a little bit on in lab on Monday about how we can never have, we'll never get exactly back to where we were in terms of a concentration, but we can get pretty close depending on what our value of K is. Okay. So here we have this reaction for ammonia. Now they're telling us that ammonia is a product. It also gives us equilibrium concentrations. So it gives us equilibrium concentrations, and it gives us Kc. Suppose some NH3 is added to the mixture, so the concentration is increased to 3.65. So increasing the concentration of NH3, which direction is that going to shift our equilibrium? Toward the reactants or toward the products?
Reactants.
Yeah, we're adding a product, so this is going to shift to the reactants. And we can always confirm Le Chatelier's principle by looking at Q. And so Q, well, they're telling us that the concentration of our ammonia is 3.65 molar, that quantity squared, divided by the concentration of N2. It says it hasn't changed, right? So that's 683. And then H2, 8.8, and that's cubed. When we calculate Q, Q, remember, is at a non-equilibrium position. And so, sort of the instant that we increase that concentration to 3.65 molar, that's when we calculate Q. We don't calculate Q once it's already reached equilibrium, once it has shifted. We calculate Q at the instant that that has been added. And so 3.65 quantity squared divided by 0.683 divided by 8.80 cubed gives us a Q value of 0.02 86. And so Q is greater than K. Here's our K value, just as a reminder, 2.37 times 10 to the negative third. And so this is larger by a factor of 10 almost, right? So this is quite a bit different. Q greater than K, that means we have too many products. So that means we are going to shift to reactants. And so, that's just sort of our verification. Right? So we can use Le Chatelier's principle to predict which way it's going to shift, and then we can use the mathematics of QC and KC to sort of confirm those suspicions. When we talk about changes in volume or changes in pressure, right, this is the one where we look at the side with the fewer moles of gas. And so over here, we have 2 moles of gas. And on this side, we only have 1 mole. And so if we increase the pressure, which direction are we going to shift?
Left.
Go ahead.
I just said left.
So if we increase the pressure, the reaction is going to try to decrease the pressure to make up for it. In order to decrease the pressure, we need less gas around, right? We need to get rid of some gas. And so in order to, if the external stress, let me change this to the external stress is an increase in pressure, our reaction is going to shift to try to decrease the pressure, to get it back towards what it was before. In order for the system to decrease the pressure, we need to shift toward the fewer moles of gas. And so in this particular example, it's the right, since it only has 1 mole, but each reaction is going to be different on which side has more moles of gas. And so we're going to write this not in terms of reactants and products, but more moles of gas, fewer moles of gas. Right? If we decrease the pressure, that's exactly the opposite, right? Decreasing pressure, the system is going to try to bring the pressure back up. It does that by shifting to the side with more moles of gas. So those are really the only 2 changes for pressure, right? But what about volume? Well, we know a little bit about the ideal gas law. If we increase volume, what happens to pressure?
Decreases.
Yeah, volume goes up, pressure goes down. And so these 2 are kind of tied together, right? And so this is going to be more moles as well. And then if we decrease volume, well, these 2 are tied together. Decreasing the volume increases the pressure. And so we're going to go to the side with fewer moles of gas. Okay. So here we have some equilibrium systems. Right? We're going to increase the pressure / decrease the volume on the system, not changing temperature. So increasing the pressure. A, which way is it going to shift?
Left.
Right.
The right.
Yeah, to the right. So here we've got 3 moles of gas. Here we've got 2 moles of gas. We don't care about these because they're solids, right? And so increasing the pressure, we want fewer moles of gas to try to bring that pressure back down. And so for A, we're going to shift to the right. How about for B? increasing the pressure for B?
Left.
That's it. We have 1 mole versus 2 moles. And then for C, the last one,
Since the moles are equal, does it not shift?
yeah, we will see no shift here. Right? Absolutely. So the pressure one is maybe a little bit harder for us to wrap our minds around, right? But if we are increasing pressure, if that's our stressor, the system reacts by decreasing pressure, and the only way that the system can do that, the system can't change the volume of the container, right? But the system can remove some moles of gas from the container by shifting the equilibrium to the side with fewer moles of gas. All right, so this last I seem to have skipped a slide here. Let me see. Oh yeah, there we go. So changes in temperature. So we did changes in concentration, changes in pressure and volume, changes in temperature. So we said yesterday that if it's an exothermic, is heat a reactant or a product if it's exothermic?
Product.
Yep. So heat's a product if it's exothermic. If it's endothermic, just the opposite. Heat is a reactant. And so I'll put delta T here, exo, endo. So if our temperature goes down, remember we want to try to heat it back up, right? Our external stress is the temperature going down. The system responds by heating it back up, right? And so if it heats it back up, which direction are we going to shift for exothermic? Toward reactants or toward products?
Products.
Products. We want more heat, all right? Which means it must be reactants for endothermic. The opposite is true if we increase temperature. We want less heat, and so the exothermic reaction are going to go to reactants to get less heat. And endothermic are going to go to products to use up some heat. Okay. I'm going to put over here in a big asterisk, right? This is the only stress that changes K, right? Since since K is temperature dependent, changing the temperature is the only stressor that will change K. All right. This last slide talks a little bit about catalysts, right? Catalysts don't change equilibrium at all because they change the forward and the backward exactly the same, right? So just real quickly, catalysts do not shift equilibrium. Okay. All right, that's the end of chapter 14. I kept you an extra minute. My apologies. I hope you have a wonderful Wednesday.
Thank you.
Thank you.
Thank you.
Dr. Davis, I have a question. I emailed you about it, but